All right, so you want to talk about neural networks. I mean, you even sent in some Java code. That's pretty cool.
Yeah, it's awesome to see someone actually diving into the code and not just the theory.
For sure. And honestly, when you look at the code, it can seem kind of intimidating, but the basic idea behind it, the neural network itself, it's pretty intuitive if you think about it like a brain, but for a computer learning from all this data.
And you can get some seriously impressive results even with a relatively straightforward setup. That's what's so cool about this. And that's actually what we're going to be doing today, breaking down that code you sent, like step by step to see how it all works.
Before we get into the actual Java, can we just take a quick high-level look at how your neural network is set up? I'm seeing three layers, right? Input, hidden, and output. Could you walk us through those?
Yeah, sure. So imagine like a really smart spam filter. The input layer, that's where you'd feed in like the raw data, the words from an email. Think of it like the ingredients for like a recipe.
Okay, I'm with you.
Then the hidden layer, that's where all the really interesting stuff happens. That's where the network is like mixing and transforming the data. It's like a chef following the recipe, I guess.
I like that, a chef and a recipe.
And finally, you have the output layer. That's like the final dish, right? So in this case, it would be that prediction. Spam or not spam?
That's a great analogy. So the hidden layer is like where the magic happens, right? You mentioned these things called nodes. They're like tiny little calculators, right?
Exactly. Each node takes in input from the layer before it does its calculation and then spits out, well, sends its output to the next layer, like an assembly line, right? Each worker does their thing.
Gotcha. Okay, so I see you've got these nodes set up in your hidden layer, but then you've also got this whole section for weights and biases. What's the deal with those?
So weights, those are the connections between the nodes. They determine how much one node can influence another. Some connections are like superhighways. Others are like those tiny back roads.
Okay, I see.
And biases, they're like these little nudges that let a node let it fire even if its input is zero, like a base level of excitement. Yeah.
And I noticed you set up your weights randomly. Any specific reason why you didn't they make them all the same?
Good catch. That random initialization is super important for the network to actually learn properly. It's like starting a race with everyone in slightly different spots, right? If they all start at the exact same place, no one would ever win.
Makes sense. So once we have the weights, the biases, and those inputs, we got to do something with them. That's where the sigmoid function comes in, right? I'm looking at your code here. Sigmoid equals 1 plus SBSX. Can you break that down a bit? What's it doing?
Don't worry, the math isn't as scary as it looks. Basically, the sigmoid function takes the output from each node and squishes it, kinda, between 0 and 1, like a dimmer switch controlling how strong the signal is.
So it's not just a huge range of values. Everything gets squeezed into that nice 0 to 1 range. Why is that so important? What does that do for the neural network?
That squishing, that's what creates nonlinearity. It basically lets the network learn these like really complex patterns. If everything was linear, we'd be stuck with only the most basic stuff.
All right, so we've got nodes doing these calculations, all these connections influencing each other, and the sigmoid functions squishing everything down. How do you translate all that into Java? I mean, how does this actually work in your code?
So the first thing is that neural network class. That's your blueprint, your foundation for the whole thing.
And inside that class, you have a constructor. That's where you set up the initial structure.
Yeah, exactly. You're telling it how many nodes for each layer, and like you noticed before, you're setting up those random weights and biases.
Now, there's also the sigmoid method that's just putting that formula we talked about, the squishing formula, into action, right?
Right on. You got it. Takes a value, squishes it between 0 and 1.
Okay, now we're getting to the main event, the predict method. That's where all the action is, right?
Yeah, this is where the data is actually flowing through the network, from input all the way to that output. You're simulating the whole process of the data changing step by step.
So taking those input values, pushing them through that hidden layer, using the weights, the biases, then squishing it all with the sigmoid function, and out pops the prediction.
Exactly, like watching that recipe come to life, each ingredient perfectly measured and mixed together to make that final dish.
Now, before we go any further, I want to point something out that I think is really important for everyone listening to understand. Your code is awesome. It shows these core concepts, but there's a key limitation. It can't actually learn from the data yet. There's a missing piece.
You're totally right. It's like a car without a steering wheel, right? It can move forward, but you can't control where it goes. That steering wheel, that's backpropagation.
So how does backpropagation work, and why is it so important for a neural network to actually be able to learn?
Well, that's a fantastic question, and it leads us perfectly into the next part of our deep dive.
Okay, so we've got like the basics down. We know how your neural network is structured, how the data flows through it, even how that sigmoid function shapes the output, but it's still kind of static, right? It's not really...
Yeah, it's just crunching numbers, not getting any smarter.
Exactly, and that's where this backpropagation thing comes in. It's like, Honestly, one of the most brilliant parts of how neural networks actually learn.
It's like adding a feedback loop, so it can actually like adjust itself and figure out if it's doing a good job or not.
So walk me through it. How does this back propagation thing actually work?
Oh, let's stick with that spam filter example, right? So you feed the network a bunch of emails, but these are emails we already know the answer to. They're labeled as spam or not spam. This is our like training data.
Okay, so we know the right answers for these emails.
Yeah, yeah. And the network, it makes its predictions, and then we compare what it guessed to the actual label. That difference, that's the error.
Makes sense. Big error means it's way off. Small error means it's getting closer to the right answer.
Now, here's where it gets really cool. We take that error and we use it to adjust all those weights and biases we were talking about earlier. So remember those weights, the connections between the nodes, telling them how much influence they have on each other.
So if the network makes a big mistake, we go back and tweak those weights and biases, try to get it on the right path for the next time.
Exactly. And we do this by like propagating the error backwards through the network, layer by layer, starting at the output and going all the way back to the input.
Kind of like retracing your steps if you realize you made a wrong turn somewhere.
Exactly. Perfect analogy. And as we're going back, we're tweaking the weights and biases just a tiny bit each time, basically fine-tuning the network's calculations so it can do better next time around.
I'm starting to see why you called backpropagation the steering wheel. It's like the network is constantly adjusting its direction based on how well it's doing.
Yeah, and the amazing thing is with every round of training, it gets a little better, a little more accurate.
Now, looking at your code, I'm realizing that coding this backpropagation thing from scratch, that seems really complicated. It's like trying to build an entire car engine by hand.
Oh, it definitely can be. That's why for, real-world applications, most developers will use these awesome libraries that handle all that complexity for you.
Like those ones you mentioned earlier, deep learning, 4J, TensorFlow, and PyTorch. So for someone using Java, like what are the pros and cons of each?
Good question. So deep learning 4J, that's built entirely in Java. It's like a really smooth fit into a Java workflow.
So if you're already working with Java, that's a big plus.
Absolutely. But TensorFlow, even though it was originally a Python library, it's got really good Java bindings now. And it has this like massive community, so many resources available, which is super helpful.
So deep learning 4J if you want that easy Java immigration, and TensorFlow if you want a more robust ecosystem. What about PyTorch?
PyTorch is another Python library, also with Java bindings. It's known for being super flexible, and it uses this dynamic computation graph, which is a real advantage for research and stuff.
So if you're like pushing the boundaries, PyTorch might be the way to go.
It could be. But, and this is really important, even if you end up using these libraries, understanding the core of backpropagation is still super valuable.
It's like you don't need to be a mechanic to drive a car, but knowing how the engine works makes you a much better driver.
100%. You can troubleshoot problems better. You can actually choose the right library for the job. You might even be able to contribute to developing new techniques.
So let's recap. We started with the basic structure, those 3 layers, the input, hidden, and output layers. Then we talked about nodes, those weights and biases, even how that sigmoid function pushes things down.
And then the coolest part, backpropagation. The thing that actually lets your network learn from its mistakes.
And we even touched on those awesome libraries like Deep Learning 4J, TensorFlow, and PyTorch, the things that help you build these super sophisticated networks without having to code every single detail yourself.
And we're still just scratching the surface here. Neural networks are a huge field and it's constantly evolving.
But even with these basics, you've got a really strong foundation. You can start digging into those libraries, messing around with different network structures, and even start thinking about how you can use this to solve real problems.
And that's what I love about this field. The possibilities are endless.
Yeah, it's pretty amazing. I'm curious, what are some of the coolest applications of neural networks that you've seen or that you're like most excited about? Yeah, it's crazy to think that just a couple years ago, this stuff was all like super niche research stuff, and now it's everywhere. I mean, self-driving cars, personalized medicine, all sorts of things use it.
It's amazing how much things have changed, right? I think one of the coolest areas, personally, is image recognition, using neural networks to actually, like, see things.
Oh yeah, those apps where you can point your phone at a plant and it'll tell you exactly what it is. It's like magic.
Yeah, it does feel like magic, but really it's all about pattern recognition. The network has been trained on these huge data sets of pictures that are labeled. So it learns how to spot these tiny little differences that tell one plant from another.
So it's like the network builds its own like visual dictionary, like a botanist, but a computer botanist in training.
Exactly. And the more data it gets, the better it gets at understanding what it's seeing. And it's not even just identifying things anymore. Now we have networks that can create completely new images, like making art and designs that no human could even imagine.
That's wild. It's like we're giving computers a sense of creativity.
In a way, yeah. And it brings up some really interesting questions, right? Like, what does it even mean to be creative? What about consciousness?
Now we're going deep. But I think, it's important to remember that even with all this, neural networks are still just tools. And like any tool, they can be used for good things or bad things.
Absolutely. That's a really important point. It's our responsibility to make sure these powerful technologies are developed and used ethically. We need to be really thoughtful about how they could impact society.
So it's not just the technical side, it's about the bigger picture, the impact.
Exactly. And that's why it's so important for people like you, people who are learning about how this stuff actually works, to be part of the conversation.
Because the more we understand how neural networks work, the better we'll be at dealing with all these ethical and societal challenges.
100%. So before we wrap up, I want to come back to that Java code you sent in. It's such a great starting point for understanding all of this.
And even though it doesn't have that backpropagation piece yet, it's still a solid foundation for, building more complex networks in the future.
Exactly. You've got those layers, the input, the hidden, the output, and the sigmoid function all working together.
And now that you understand backpropagation, you can start figuring out how to add that learning piece into it.
You could try different activation functions, go around with the network structure. You could even try incorporating one of those libraries we talked about.
It's like a whole new world of possibilities has opened up.
And I have a feeling this is just the beginning for you. So here's something to think about.
The big question you've been waiting for all episode.
If this simple network can do all this, what could you create if you added backpropagation? Real-world data. What if you used the power of those advanced libraries? Think about the problems you could solve, the things you could invent.
Yeah, like the world of neural networks is your oyster. Go explore it, play around with it. Who knows, maybe you'll be the one to build the next big thing, something that changes the world.
Keep learning, keep pushing the boundaries. And most importantly, have fun with it.
That's all for this deep dive into neural networks. Thanks for joining us.